Hi everyone, this is John Wen. Today is July 8th, 2020. In today's video, I'm going to go through the updates of the progress about my research item since the past week. So you can see from the highlights, there are two items in my work stack. The first one is to extend the survey to journal version. The estimated progress is about 5%. And also the deep learning workflow, and the estimated progress is about 5% as well. So let's get into the detail. Firstly, let's look at the progress or the update of the extend survey to the journal version. So since the past week, I refined the WRPS pseudocode and updated the DBDSB, the pseudocode. And many thanks to Dr. Lu's feedback. I make some mistakes, but I think it's been fixed at this moment, and hopefully we can go through that together and see if there is any further we can change. And the third item for this extension is I wrapped up the initial version of the 5.1 section, which is the goal of the scientific workflow management system. So let's take a look at the paper. So for here, this is a pseudocode of the WRPS algorithm, and basically what I made the change is about the failure handle. Basically, I think there is one more condition check. For here is if the rest of the when any task or pipeline meets a deadline during the execution, we also need to do another check to check whether the rest of the task or pipeline in the same VM can still finish the execution before the deadline. If not, we are going to put this task or pipeline back to the execution queue or scheduling queue with updated deadline and go to the line 4. And another change is after we wait until all the tasks in the the scheduling queue finish their execution, and we will release their child, and at the same time with updated deadline on the child. So basically this updated deadline is can indicate that the child will be updated the deadline before they put into the queue for the execution. So this is for the WRPS, and let's take a look at the DBDS. So for the DBDS, I mainly work on the DBDSB algorithm, and which is I think there is some mistake from the last time, because it seems if I did in the previous way, the second part will be sequential, and this whole part will be sequential. But actually, we are able to if we take a look at the paper for the algorithm 2, if I zoom this a little bit out, and you can see from this algorithm 2, the while loop will basically schedule to find all the idle VMs and then to pop up the task from the priority queue, and then to schedule the task on the idle VM. And firstly, this while loop will be done first, and after that we will wait for the task to finish on the VM, and then update the child on the queue, as well as we will insert this VM back to the idle virtual machine. But this algorithm still has an issue, because we will do the while loop first. That means we will loop through all the idle VMs and assign some task on each of the VMs here, but we only keep one V and one T. At the end of this loop, we only keep the V and T for the last task and last VM, right? But these lines here only work on the T and V. That means these three lines, line 13 to line 15, will only be occurred on the last task and last VM. But that's not actually true, because we have to free all the VMs in this while loop and we will do all the updates for the child in the task in this while loop as well. So basically this will be applied to all the t and all the v. So that is one thing I noticed, and in our algorithm I think I made that more clear. So basically the same thing, we will do the while loop first, and we will dequeue the task and do the assign the task to the idle virtual machine. And then what we will do is we will do in parallel, and we will check every task in current running tasks, and we put all the tasks into this current task item, and then we are going to parallelize operating on every task in this set. Basically we are going to wait until each task to finish the execution, and then we push the child of this task to the priority queue, and then we mark the VM back to the idle virtual machine. So I think this way may be more accurate to express the idea of the original paper. So this is the second item, and the third item is I worked on this part, the goal of the scientific workflow management system. Basically I wrapped it up with the first version, and basically it contains 3 subsections. One is automate and distribute the workflow execution, and second part is talk about the service level agreements, and as well as the quality of the service requirements. And the third subsection is to talk about real-time monitoring and failure handling. So I think the 3 parts has been initially finalized, and we can modify based on what we have right now, or we can add more, or delete some of them if not necessary. So that's the first item, to extend the current paper to the journal version. And the second part is about the deep learning workflow. And the first one I hope to mention is I reproduce a simple neural network in KUDA. And basically this is a video that Dr. Liu forwarded to me a while ago, maybe a few weeks ago, and it's about KUDA neural network. And maybe at the 90% of this video is talking about a simple KUDA program, or simple KUDA example, that is to adding 2 arrays together. The rest of 10% is this guy go through a source code of a very simple 1-layer neural network that is able to work on the eras data set. So basically I download the source code, and also I reproduce the execution. Basically this is a code I download from online, and basically this one is quite similar to what we have seen before for the KUDA code. Basically it has several kernels, and these kernels are doing different things, like the matrix subtract matrix, or different like methods like sigmoid, etc. So basically this main, let's take a look at the main method. In the main method it has a very small sample of data, and basically this one will be used for training. And if we take a look at the code, basically we'll do some call some kernels at the main function, and it will do the KUDA malloc, basically add malloc some memory on the device, as well as do the memory copy, etc. So these things are quite similar to what we have before, and then it will do the updates weights, and also to prepare the delta to do the back propagation. So this is a very simple example. I haven't spent too much to read through the code. I just reproduce the execution. So if we take a look at the execution, and we can compile, we can compile this one with this option, because we have to specify the architecture. If not, we will get some errors. That's what I discovered. If we delete this one and use a normal compile code, and we will get some error, because it requires architecture is newer or greater than at least 35. So we have to specify the architecture to more than 35. So I use a 50 that is just fit for my current hardware. And also we allocate code to true, and then we can compile this code. So after compile this code, we can run it, and you will see the result. So let's run the code, simple new run.out. And basically, as you can see, we only do the training, and this training is going to have four data or 4 tuples. So basically, we're going to get some error numbers. We're going to get some prediction numbers, and this is basically how it works. And hopefully, I will get more time to read through the code and see if it's exactly aligned with a single level neuron, how it works. So that's a plan. And also the second item is I keep learning the KUDA in the past week, and basically there are several things to worthwhile to point out. First, I firstly know about the pin memory, and like the zero copy memory and unified memory or managed memory. So basically, in the previous way we are doing in such architecture or such diagram, basically we are communicating from the CPU and GPU, but for both CPU and GPU they have their own memories, and basically they are transferring between the PCIe, and you can see the speed is comparable, very small, than the inner memory transaction. And but actually how it works is whenever we need transfer some data from GPU to CPU, but on the CPU side, on the host side, firstly we always have the pageable memory, because in host, when we use a malloc function to allocate some memory on the host, it's always pageable memory, because it can be locked by page. And what the KUDA will do is, firstly it will convert this pageable memory to a pin memory in the host. So basically you can see this step is implicitly handled by the KUDA driver, and then this pin memory will have the full control by the device, and device can read from this pin memory. Because pageable memory, the device does not have the full control on this pageable memory. So what KUDA will do is to duplicate this pin memory first and then do the transfer. So based on that, we have another type of memory called the zero copy memory. And basically, for most of case, by the way, for most of case, if we can create a pin memory directly instead of create the pageable memory at first step, we create this one directly, the performance always will be improved based on what we have. And second type is zero copy memory. That's a special pin memory, and which is going to be mapped to the device. So what does this mean is the device does not need to actually copy the data, or the device does not need to have any pointer to hold any data. So all the data is on the host side, but we are going to map this one to, we are going to because you can see it's called a zero copy memory. So it's a mapped memory from the host. So every time when the device is going to need some memory, it will load on the wrong time. So load from pin memory on time. So that's called a zero copy memory, which is very good at use when the device does not have sufficient memory load or does have sufficient DRAM. And then you can put all the things on the host. But you can see from this table, the zero copy memory will always have much more time execution than the normal memory or the device memory. If we copy the device memory, means we will copy the data to the memory. So you can see this column is always greater than this column. And third type is very interesting. Is from the KUDA 6. There's another feature for the KUDA that's called a zero. Oh, sorry, that's called the. I think this is the typo. It should be called the managed memory, which is a special feature for the KUDA 6. Since from KUDA 6, which is going to have. We are able to specify the managed memory, which is going to be accessible from both host and device at the same time. So it's not the same as a zero copy memory, and because we don't specify this pointer at all, or whether it's on the host or whether it's on the device, we don't specify it, but it will it's just like a pool, and this pool will be automatically accessible by host and device at the same time. So if we use a CUDA malloc managed, and this pointer will be able to access by both host and device. So in this way, we will simplify a lot on the coding. So that's why this one is currently used a lot in the CUDA programming, and a lot of things will be implicitly taken care of under the hood or by the CUDA runtime to transfer the data or do other things. So this is very interesting to keep learning the CUDA, and I think that's pretty much to the updates from the last week. And thank you so much for your time, and hopefully you enjoyed the video, and until next time, happy coding.